Hi everyone, so today we're going to be looking at rate law today, and we're going to look at the effect of the concentration that it would have on the rate. So one way that we can study the effect of the concentration on the rate of reaction, we can determine the way in which the rate at the beginning of a reaction, not beginning of a reaction, which is our initial rate, it depends on the starting reactant concentrations, which is our initial concentration. So we're going to look at the equation, and that's going to be able to show us how the rate depends on the initial concentration of the reaction, which is called our rate law. So we're going to be looking on that initial concentration. So for a general reaction, there you can see the following equation. These large or uppercase letters, those are our reactants. And the lowercase are our coefficients. And our coefficients are used to balance out the equation. So when we look at the rate of reactions, it is going to be proportional to the products of the initial concentration of the reactions, or the reactants. So when we look at the rate law, its general form, we have rate equals K is constant, and our constant, it does vary with temperature, and it's also known as like a rate constant, so it's going to be unique for each reaction, and it must be found experimentally. And then the remainder are exponents that are found in our rate law. These can't be obtained from the balanced equation, and so they can only be also determined experimentally. So those are a few important points that we have to take a look at. So the X and Y, which we mentioned are exponents, are referred to as the order with respect to the reactant, which is our reaction orders. And then the exponent, which is our orders, are determined, as I mentioned, experimentally. The exponents, which are our orders, they are going to give us an overall order. So, and our overall order is the sum of the exponents with respect to the reactant in the rate law. So when we look at this rate law that we are seeing above, we're going to put it into a rate law equation. The order with respect to Cl2 is 1. And the order with respect to H2 is also 1. So the overall order is 2 because we are adding them all up. So it's a sum. It could also be known as the total order of reaction. It just depends. So in your textbook, you might see total order of your reaction, but the overall order is the sum of our orders. So if we look at this rate law that we just saw, if it doubled the concentration of CO2, what do we think would happen to the rate? So if we doubled only CO2, then we're doubling the rate. So you can see that we are now doubling that constant. So if we look at the rate law, if double the concentration of H2 and Cl2, that means it would be doubling both. Okay, so now we doubled the entire thing, so now it's 4. So the rate increases by a factor of 4, which is quadrupling the rate. Okay, if we look at this rate and if we triple the concentration, we are tripling the rate. Okay, so we have to look at it, this is the tripling the rate of H2, we would triple it. So it really depends on what we're looking at, but if we are doubling only 1, we would put a 2. If we're doubling the whole thing, we have to put a 4 because it's quadrupling it. If we're only doubling or tripling 1, it just depends, but we are tripling or doubling that entire rate. So we're gonna look at the rate law for the following reaction here, and has been determined to be a rate of KNO2H2. So what are the orders with respect to each reactant, and what is the overall order of the reactants, or the reaction? So for H2, okay, it is 1, because there's only one of them, okay? In order for NO, it's 2. So if we add those both up, it is 3. So the order of our reactant is 3. So what would happen to the rate if we double the concentration of NO? So if we were to double that, okay, we're doubling it now. So this 2 was based off of our constant in front. So this 2 was because there was 2 NOs. So there's 2 of them. Okay, so there's 2 NOs. So now, because we're doubling it, okay, that means it's going to be quadrupled. So that means there's going to be a 4 in front of here because we are quadrupling it because we're doubling the concentration of NO. So NO times 2 is 4, so that's how we know that. And what changes now is that this 2 is gone because we're doubling the whole thing. And we had to quadruple it. So would it make sense to have this 4 here if that 2 was still at the top as an exponent? Okay, so we have to remove that. Now, what would happen to the rate if we tripled the concentration of NO and doubled H2? We would take our original rate that we had, and we would now triple the concentration of NO and double H2. So that means we would get 18. So we put all that into the calculator, we would get 18. Now, what would happen if we decrease the concentration by half? That means we're gonna put half where our NO would be, and based off of that, it would be 1/4 of our rate. So we would decrease it by a factor of 4. So you can see that there's different ways that we can determine the overall order based off of the rate. So if we either double, triple, whatever it might be, we have to take all that in consideration. So when we look at elevated temperatures of HI, it reacts according to the chemical equation as follows. So the hydrogen and iodine split up. At 443 degrees Celsius, the initial rate of the reaction increases with the concentration of HI as shown below. So this table is given to us with our initial rates of all the following. Okay, so we can see all of that there. So we're going to determine the rate law, what is the order and overall order, and calculate the constant rate and its units. So, based off of the following information that is given, since we're only given one reactant, which is HI, the proposed rate law is going to be KHI and then unknown exponent. Okay, that is what our rate law is going to be written out as. So we need to know how to write that out because rate law is based off of a reactants. So now we're trying to see how the initial concentration of HI will affect the initial rate of the reaction. So we're going to try to calculate X because we don't know what X is. So we're going to pick any 2 reactions here based off of our experiment, and we're going to compare how they change in concentration of HI and how it will affect the rate. So we're just going to pick any experiment, doesn't matter. So we're going to pick 1 and 2, for example, here. And you can see the following information. HI, the initial is 0.0050, and then the rate is as follows for experiment 1 and 2. So now we're going to set up our ratio. So this is going to allow us to see how the change affects based off of experiment 1 and experiment 2. Okay, so based off of this information, we're going to use the following equation. Rate 2 divided by rate 1 equals HI2 divided by HI1. Since the exponents are the same, we can easily factor them out based off of they're the exact same. And one important thing is I always place a larger rate in the numerator and then the smaller in the denominator. Okay, so that is just what we do. So based off of this information, we're going to factor out the X. So the X is on the outside of the brackets now, and we're going to have the larger rate as the numerator. So based off of this information, we sub our values in, and based off of all this information, if we are calculating it, we would get 4, and this suggests that if the concentration is doubled at the rate, increases by a factor of 4. And then this 2x, so what we're going to do is we're going to make the left side of the equation equal to the right side of the equation. So we're going to put x as 2, and therefore it's going to be equal to 4 now. So left side equals right side. So therefore we can determine the rate law is at a factor of 2 because of what we just found of equaling left side versus right side. So the order with respect to HI is 2, and the overall order is 2. That is based off of the information that we found, subbing all of it in. Now, we have to calculate the constant, or the rate constant and its units. So, based off of the experiments given, we're gonna take, once again, any of our experiments. We're gonna take the rate and then we're gonna divide it by its initial. From there, we're gonna divide it out and we'll get K as 30. So now we need to find the units because we can't just leave it as 30. So the rate is in moles per liter per second, and then the initial was moles per liter. So if we were to divide everything out, we will be left with liters per moles per second. And so therefore, that is the unit that we will be using for B. Okay, this unit might change depending on the experiment used. So we need to make sure that we divide it out, okay? And we can use this process to divide it out. So if you wanna save this, you can, okay? It's easy also to kind of figure out how do we figure this out. We kind of just cross things out as time goes on, and you can determine how it is written. So liters is gonna be on top, and then moles times our seconds is going to be on the bottom based off of the information. So now you are able to look at the next example here posted. I want you to try this out on your own, okay? This is the rate of the reaction again, given based off of the following information. I want you to try it out. Pick an experiment to compare, determine the rate law, calculate the constant, what is the order and the overall. Okay, so pause now and try it out and see what you can come up with. Okay, so based off of this following information, I want you to check your work, see if you were able to figure it out. Because there's two reactants, we had two parts to our rate law. So we have NO and O2. We have unknown exponents. So we need to figure out how NO affects the rate of O2 by calculating the X and Y. So you start off by calculating the X, finding two experiments that you want to use. It could be any experiment. The reason why we chose these two is because that the O2 were very similar. So that is why we picked those two. And then based off of that, we were able to plug in the information and find out what X means. So X is 2. Then we calculate Y, same sort of thing. We look at our NOs. We found out that they're very similar, so we use those two values. And we found Y is 1. Then we were able to find the rate based off of only one experiment. And we found the units of measure. And then the order is based off of the following. So because there was 2 NOs and 1 O2, based off of our information, that means our overall order is 3. So we're just adding up the sum of our exponents. When we look at what happens to the rate if A is doubled for NO and is tripled for O2, we put that following information into our rate, so doubled and tripled. If we multiply it all, we will get 12, and so therefore it would increase by a factor of 12. It could decrease depending on the experiment, so if we decrease it, just do note that most of the time it does increase, but there are chances that it will decrease. And then the last part is calculate the rate of the reaction if NO is 0.030 moles per liter and O2 is 0.10 moles per liter. So now we're just taking all of our information and plugging it in. So we know what our NO is, we know what our O2 is, and our K's are constant, what we found before, which is our 7,000. And from there, we're able to calculate it. You can write it as this way or this way. Both are acceptable. And based off this information and finding our units by canceling things out, that is our rate. So there is another example here if you want to take a look at. This is a hypothetical one. Once again, you're more than welcome to go through these to take a look at them and determine the rate law for all of these to try it out. All of these are great examples to practice and determine the overall rate. Few things to take into consideration is that we can use graphs to determine the order of a specific reactant. So we could have a 0 order. That's where the reactant does not affect the rate of reaction, and therefore the rate is proportional, okay, to our initial, and so it is 0. We could have a first order where A and the rate go up or down by the same amount, so rate is proportional to A. Okay, and it is a 1. Or we can have a second order where if we times it by 2, then the rate increases by a factor of 4. Okay, so it's proportional to our initial rate at a factor of 4.